Imagine for a second that you are managing a team of brilliant researchers. Like, they are absolute geniuses,
Okay, I'm picturing it.
but, you've instituted this one bizarre, incredibly strict rule. They are completely forbidden from sharing their notes with each other.
Wow, okay. That sounds counterproductive.
Exactly. So every single time you ask this team a question, every single researcher has to individually pull down, like, the exact same 10,000-page encyclopedia.
Oh, man.
Right. They have to read it cover to cover, process all that information completely from scratch, and only then can they even start working on your specific question.
That is just a colossal waste of time. I mean, the energy and resources alone.
It sounds incredibly frustrating, right? But the crazy thing is, that scenario, that is exactly how today's most advanced AI agent workflows currently operate.
Yeah, it really is. It captures the central bottleneck perfectly, actually. Because, we have these incredibly sophisticated language models now, but the orchestration layers we use to make them work together, which are frameworks many of you are probably deploying right now, they are surprisingly inefficient at managing shared context.
And that inefficiency is the exact focus of our deep dive today. We are looking at this fascinating state-of-the-art foundation paper. It's out of the National University of Singapore.
Right.
It's titled Efficient LLM Serving for Agentic Workflows, a Data Systems Perspective. And basically, our mission for this deep dive is to unpack a new system they've developed called Helium.
Helium, yeah.
Yeah. And Helium solves this massive inefficiency in AI teamwork by, well, essentially borrowing decades-old architectural tricks from traditional database management. And by doing that, it dramatically reduces compute time and memory overhead.
It really does.
Yeah.
But, to understand the mechanics of Helium, we really need to frame this specific problem with what we call agentic workflows first.
Right, let's establish that, because we aren't just talking about a standard chatbot anymore, are we?
Exactly. We have moved way beyond the single prompt, single response chatbot paradigm. I mean, we are now building these complex systems where multiple AI agents interact autonomously to solve much larger goals.
Give me an example of that for those listening who might not build these every day.
Sure. So consider a map-reduced pattern. You might feed a massive input document into a system, and the system maps it out to, say, multiple concurrent expert agents.
Okay, so they're working in parallel.
Yeah, exactly. They analyze different chunks of the data at the same time. And then a final summarizer agent reduces those parallel analyses into one cohesive output.
Oh, I see. Or another one I've seen is the multi-agent debate architecture,
Oh, yeah, that's a great example.
where, like, an initial draft generated by one AI is actively critiqued and iteratively refined by several other AI agents, and they're acting as, like, adversarial reviewers.
Precisely. Now, in those scenarios, you have multiple distinct agents constantly querying the exact same underlying source material.
Right, the base document or the initial draft.
Yeah, they are operating on the same core data. But standard orchestrators, things like LangGraph or AgentScope, they treat each of those queries as entirely separate, isolated events.
And the researchers at NUS, they have a specific term for this, right?
They do. They diagnose this specific issue as operator-level myopia.
Operator-level myopia. That's a great phrase.
It really is. Modern serving engines like VLLM and the orchestration framework sitting on top of them, they all suffer from this short-sightedness.
So they basically can't see the big picture.
Exactly. In data systems terminology, they treat each individual call to the large language model as a black box user-defined function, or UDF.
The black box.
Right. Historically, in relational databases, if you wrote a custom UDF, the database's query optimizer could look inside it to see what was actually happening. It just executed the code blindly.
Interesting.
And current AI orchestrators do the exact same thing with LLMs. They have zero visibility into the actual computational overlap happening inside the model.
Okay, so we are back to my kitchen analogy. It's like a restaurant kitchen where the head chef, the sous chef, and the pastry chef are all cooking the exact same base chicken stock from scratch.
Right.
And they are doing it on separate stoves because the kitchen manager, which would be the orchestrator in this case, only sees the final ticket, like make soup, make sauce, make risotto.
Exactly.
The manager has myopia. They can't see that all three of those tickets require the same underlying stock.
That is spot on. The orchestrator just issues the commands, like Agent A, process this document. Agent B, process this document.
And the engine just does it.
Yeah, the serving engine dutifully spins up the compute and blindly processes the identical document twice.
But wait, let me push back on this a little bit, because if you are listening and you run these systems, you might be thinking, don't modern AI serving engines already have prefix caching to prevent exactly this?
It's a very common misconception.
Right, because systems like VLLM do cache prompts. Like if you send the same system prompt or the same document multiple times, the engine is supposed to recognize it, right, and pull it from memory rather than recalculating it from scratch.
So, yes, prefix caching does exist, but the implementation in engines like VLLM is entirely passive. It's opportunistic.
Passive, what does that mean in this context?
It means it relies on an LRU eviction policy, least recently used.
Oh.
The online serving engines are designed to handle unpredictable streams of queries from multiple users concurrently. They only have a finite amount of VRAM, GPU memory.
Which is incredibly expensive.
Exactly. So they have to constantly clear their key value cache, the KV cache, to make room for new requests.
And just for a quick refresher, the KV cache is where the engine stores the heavy mathematical representations, right?
Yes, the key and value attention vectors of previously processed tokens, so they don't need recalculating.
Right, because the bimodal nature of LLM inference makes recalculation a massive issue. You have the prefill phase, where the model ingests and processes the prompt, which is incredibly computationally heavy and really slow.
Right.
And then you have the decode phase, where it generates the answer one token at a time, which is much, much lighter.
Exactly. So when a multi-agent workflow hits a busy concurrent serving engine, the engine's passive LRU cache just gets flooded with totally unrelated queries from other tasks.
Oh, I see.
Under that memory pressure, the system actively evicts the shared context of your specific workflow. It basically forgets it to make room.
So when your second or third agent finally executes and, asks a question about that original document, the KV tensors are just gone.
They're gone. The system suffers a cache miss and has to pay that massive computational penalty to run the prefill phase all over again.
Wow, so passive caching fails because it basically relies on the hope that your shared data just happens to not be overwritten by the time your next agent needs it.
Exactly. It's hoping for the best.
The system can't guarantee efficiency because it literally cannot see the overall structure of your multi-agent application. It just reacts to requests as they arrive in real time.
And this limitation is exactly what necessitates Helium's architectural shift. If the black box approach is failing, the system needs to see the entire application logic before it starts processing tokens.
Okay, so how does Helium actually fix this?
Well, Helium abandons the black box UDF model entirely. It elevates the LLM to what they call a first-class operator.
It's a first-class operator.
Yes. Helium adopts a foundational concept from classic relational database management systems. It models the entire multi-agent workflow as a query plan, represented by a directed acyclic graph, or a DAG.
A DAG. Okay, so for you listening, a DAG acts like a strict flowchart where data moves in one direction from inputs to outputs without ever looping back on itself.
Right.
Which means it allows the system to map out every single dependency before execution even begins.
Exactly. Before Helium sends a single prompt to the GPU, its query optimizer analyzes the topology of this DAG.
It looks at the whole map.
All right, and the very first stage of optimization is called initial plan pruning. It utilizes a technique called common subgraph elimination, or CSE.
Common subgraph elimination.
Yeah. Helium scans the entire workflow graph mathematically. It hashes the topology and the inputs of every single node, and it actively hunts for identical subgraphs.
Okay, let's unpack this. So you're saying it looks for instances where two different agents are being asked to perform the exact same computation on the exact same input data.
Yes.
So it is functioning almost like a compiler optimizing software code, but it's doing it at the LLM prompt level.
That's a brilliant way to put it, yeah.
So if Helium spots that, say, Agent A and Agent B are processing the exact same data with the exact same instructions, what does it actually do?
Well, it intervenes. Helium introduces a custom operator called catch fetch.
Catch fetch.
When the CSE phase identifies deterministic operators, meaning operations that are guaranteed to produce identical outputs from identical inputs,
Yeah.
Helium literally rewires the dependency graph.
Wait, really? It rewires it?
It completely blocks the redundant LLM call for the second agent. It strips out the expensive neural network computation entirely and replaces it with a simple, lightweight, instantaneous data retrieval from a global prompt cache.
Oh, wow. So if Agent A already analyzed the financial report and the workflow DAGs shows Agent B is scheduled to analyze the exact same report in the exact same way, Helium just intercepts Agent B's request.
Yep.
It completely bypasses the LLM and just hands Agent B the analysis that Agent A already generated.
Exactly. It turns a massive GPU-intensive prefill and decode sequence into a simple copy-paste operation.
That is incredibly elegant. So by analyzing the DAG beforehand, Helium cures the operator-level myopia. It sees the redundant work and eliminates it before a single token is even processed.
Exactly.
Okay, skipping identical tasks completely makes sense. But, I mean, in real-world agentic applications, agents almost never ask the exact same question.
That is true.
Like, if you have 3 specialized agents, they might all share a massive, say, 5,000-word system prompt that establishes their roles and the background data.
Right.
But then you append a totally unique instruction for each agent at the very end. The cache fetch operator won't trigger there, right? Because the full prompts aren't a 100% match. The outputs will be different.
You're completely right. That partial overlap is actually the most common scenario, and it's where passive caching usually falls apart.
So how does Helium handle that?
To handle this, Helium introduces cache-aware scheduling, which is powered by a very specific data structure called a templated radix tree, or TRT.
A templated radix tree. Okay, a traditional radix tree is essentially a space-optimized prefix tree, right?
Yeah.
It's like a family tree for text. So, for example, if Agent A asks for Q3 earnings for Apple, and Agent B asks for Q3 earnings for Microsoft, the radix tree merges the shared phrase Q3 earnings for into a single parent trunk in memory.
Right.
And it only splits into separate branches for the unique words Apple and Microsoft.
That is exactly how it works, and Helium adapts this concept specifically for batch workloads in LLM serving. Because Helium possesses the entire workflow DAG, it doesn't just sit around and wait for requests to arrive dynamically. It builds a templated radix tree to map out the prefix structure of the entire batch workload before execution begins.
So it knows the future, basically.
Exactly. It identifies the static prompt prefixes, those giant system prompts or shared documents, and it groups the LLM calls that share these prefixes into what it terms inner sequences.
Here is where it gets really interesting to me. It sounds exactly like meal prepping.
Meal prepping, how so?
Well, passive caching is like hoping you just happen to have chopped onions in the fridge when a recipe calls for them.
Okay, yeah.
But Helium looks at your recipe plan for the entire week. It realizes you need chopped onions for 3 completely different meals, so it chops them all at once on Sunday and keeps them locked in the fridge. Or, in this case, the GPU memory, so they are instantly ready for Monday, Wednesday, and Friday.
I love that analogy, yes. In GPU architecture terms, Helium achieves that meal prep through what they call proactive KV caching.
Proactive KV caching.
Because the TRT has mapped the shared prefixes beforehand, Helium deliberately schedules and executes the compute-heavy prefill phase for those static prefixes during the very first run.
It pre-computes them.
Exactly. But critically, rather than leaving those generated KV tensors vulnerable to an LRU eviction policy, Helium pins them in the VRAM.
It locks them in the fridge.
It locks them in place. They cannot be evicted. The cache-aware scheduler then actively orchestrates the execution order of all the remaining unique tasks to maximize the reuse of those pinned tensors.
So the scheduler isn't just taking tasks on a first-come, first-served basis.
Not at all.
It actively calculates the execution path that will reuse that shared trunk of the radix tree most efficiently.
Exactly. The scheduler utilizes a token step cost model.
Token step cost model.
Yeah, it analyzes the DAG and calculates factors like precedence delay.
What is precedence delay?
It's the amount of time certain agents must remain idle, waiting for dependent upstream agents to finish their tasks.
Ah, okay. So it's waiting for someone else to finish.
Right. And Helium Scheduler intelligently interleaves independent tasks during those exact waiting periods. It balances the load to keep the GPUs fully saturated with work while guaranteeing that the shared KV cache is never thrashed or evicted prematurely.
Okay, so we have a very clear picture of the underlying mechanics now. Helium uses common subgraph elimination and the catch-fetch operator to just bypass identical work entirely.
Yep.
Then it uses the templated radix tree and proactive KV caching to isolate and pin shared context, seamlessly orchestrating the workflow to eliminate redundant prefill phases.
That's the summary, yeah.
The architecture is incredibly elegant on paper. But, if you were listening to this and you are deploying complex applications right now, you really need to know how this impacts real-world latency and resource consumption. What happens when the pressure is actually on?
And the NUS researchers knew that, so they validated Helium against highly complex, real-world constraints.
What did they test it on?
They designed an end-to-end evaluation using a massive trading composite workflow.
Trading, like finance.
Yes. This benchmark simulates a modern, multi-agent financial firm where latency directly impacts outcomes.
I mean, a financial trading simulation is the perfect stress test, right? Because the dependencies in that environment are incredibly dense.
Extremely dense.
You aren't just summarizing one document. You have agents gathering data, agents arguing over the data, and then agents making final decisions based on those arguments.
Exactly. The trading workflow they built involves 19 distinct AI agents and requires 88 separate LLM operations.
88? Wow.
Yeah, and it's structured across 3 distinct stages. First is the analyst stage, which operates largely in parallel. You have multiple specialized agents concurrently processing massive daily data sets.
Things like market data, social media sentiment, breaking news, company fundamentals.
All of it, yeah.
And once that parallel data is processed, it flows into the next stage, the research stage, right?
Right. Researcher agents take the outputs from all those analysts and they engage in multi-turn debates to synthesize the findings. And this is all mediated by a centralized manager agent.
That's a lot of context to keep track of.
It is. Finally, the workflow reaches the decision stage. Trader agents propose specific market actions, and then risk management agents actually stress test those proposed trades through even further debate.
And ultimately, a final fund manager agent outputs the definitive investment recommendation.
Precisely.
Okay, 88 different times an orchestrator has to call an LLM, manage the context window, handle the output, and pass it down the graph.
Yes.
If an orchestrator has operator-level myopia on a workflow of that density, those bimodal prefill penalties are going to compound exponentially.
Oh, the compounding delay is brutal in standard setups. So the researchers benchmarked this entire trading workflow using the Qwen38B model.
Okay, a solid model. What were the results?
When executed on a naive VLLM setup, a high-throughput engine that simply lacks workflow awareness, Helium achieved a 39.5 times speedup.
Wait, almost a 40x reduction in execution time?
Yes.
That completely transforms the viability of an application. You are moving from waiting like half an hour for a batch process to finish down to under a minute.
Exactly. It's a game changer. But the comparison against dedicated orchestration frameworks is equally vital.
Right, because LangGraph provides structure and manages the agents.
It does. But as we discussed, it still treats the underlying LLM engine as a black box. Even when compared against a mature framework like LangGraph, Helium achieved up to a 1.49 times speedup.
So it processed the entire 88 operator workflow nearly 50% faster than LangGraph.
Yes.
That's huge. But, average throughput is important, sure. But for user-facing applications, the user experience is defined by tail latency.
Absolutely.
If an application hangs on the user's end, they just abandon it. So what does this all mean for the end user?
Looking at the benchmark data for LangGraph, the 95th percentile latency, meaning the execution time for the slowest 5% of requests, sat at 51.7 seconds.
Okay, almost a minute.
Helium reduced that 95th percentile tail latency down to 37.2 seconds.
Wow.
It dramatically tightens the variance and eliminates those stragglers that cause application bottlenecks.
So by eliminating the unpredictable cache misses of the LRU policy, Helium is providing consistent, deterministic performance.
Exactly. But the metric that, in my opinion, fundamentally shifts the economics of running these models is the memory footprint of the orchestration itself.
The overhead.
Right. To map out complex prompt structures, systems have to store metadata tracking all those cache states.
And GPU memory is arguably the most constrained and expensive resource in AI right now. Every megabyte dedicated to orchestration metadata is a megabyte you cannot use for actual context windows or batch sizes.
Exactly. A prominent baseline system called SGLang attempts to manage this using a structure called a radix cache.
Yeah.
For a complex 16-branch workflow tested in the paper, SGLang's radix cache metadata footprint ballooned to 13.8 megabytes.
14.8.
Yes. Because it tracks every single dynamic request individually, the metadata scales linearly with the number of incoming requests and the total token volume.
So almost 15 megabytes of VRAM just to keep track of the cache itself.
Right. Now, Helium's templated radix tree metadata for that exact same 16-branch workflow consumed only 552 kilobytes.
Wait, really? Just over half a megabyte?
Yes.
That is a reduction of over 96%. SGLang uses almost 15 megabytes, and Helium uses half a megabyte.
Incredible, isn't it? Helium achieves that microscopic footprint because its abstraction scales with the static workflow structure, the DAG itself.
Rather than the dynamic volume of incoming user requests.
Exactly. It maps the template once, rather than mapping every individual execution over and over.
Okay, so by shifting the paradigm from reactive query processing to proactive database-style query planning, Helium is basically approaching the theoretical limits of hardware efficiency here.
It is, and the researchers actually proved this mathematically.
Oh, they did?
Yeah. They formulated the task of scheduling these multi-agent workflows as a complex optimization problem, and they ran it through an off-the-shelf solver to calculate the absolute theoretical minimum execution time possible for the hardware.
The mathematically perfect score.
Exactly. And Helium achieved an average optimality gap of only 0.9%.
0.9%.
Its execution plans operate within 1% of mathematical perfection.
That is just, it bridges the gap between theoretical data systems optimization and the practical reality of scaling AI serving.
It really does.
The architecture of AI is evolving so rapidly right now. We're clearly moving away from the inefficiency of isolated agents redundantly processing identical data.
Thankfully.
Helium proves that by treating the workflow as a directed acyclic graph, applying common subgraph elimination, and leveraging a templated radix tree for proactive KV caching, we can completely eliminate that operator-level myopia.
We can.
We can literally rewire dependencies on the fly and pin shared context in memory, and that results in massively faster execution times, tighter tail latencies, and drastically lower memory footprints.
The core takeaway for you listening is that the connective tissue orchestrating the agents is just as critical as the neural network weights of the agents themselves. Scaling AI requires holistic system design, not just larger models.
And that structural evolution points to a much larger shift in the industry, I think. For the past few years, the frontier of AI research has been completely dominated by a singular focus on parameter count.
Oh, absolutely. Bigger is better.
Right, building bigger, monolithic, standalone models. But if systems like Helium can perfectly orchestrate 88 different operators with near-zero friction, it forces us to rethink that entire trajectory.
It does.
What if the true path to highly capable generalized artificial intelligence might not actually rely on scaling up a single, massive brain?
I agree completely.
Instead, the future likely belongs to how elegantly we can orchestrate a swarm of smaller, highly specialized, and incredibly efficient agents, all of them operating seamlessly off a perfectly synchronized hive mind memory.
Because when the underlying infrastructure can perfectly predict and manage the flow of information between those specialized nodes, the capabilities of the overall swarm just expand exponentially.
It is a profound shift in how we architect intelligence. Thank you so much for joining us on this deep dive into the underlying systems powering the next generation of agentic workflows. We'll catch you on the next one.